Hi guys, now we start Soil Mechanics Week 5. Topic 2, Flow of water through soil. From Week 5 to Week 7. Firstly, we go for the program outcomes. You may refer the program outcomes below. Alright, so these are course outcomes and COPO mapping. Learning outcomes. At the end of this lecture, students should be able to define the concept of pressure head and hydraulic gradient using Bernoulli equations, understand the definition of permeability and 1D flow of water through soil using Darcy law, and the last one, determine the coefficient of permeability K in laboratory by using the constant head test and falling head test. Pressure head and hydraulic gradient. According to Bernoulli equation, the fluid mechanics, the total head causing a water flow is given by the sum of pressure, velocity, and elevation head. You will see the equation after this slide. As we mentioned just now, Bernoulli equation states three head components for total head causing a water flow. This is the total head, and this is the first pressure head, U over unit weight the water plus V squared, which is velocity, over 2G. G is acceleration due to gravity, plus Z. Z is elevation head, which is vertical distance of a given point above or below datum. Alright guys, if the Bernoulli equation is applied to the flow of water through a porous medium, such as soil, the velocity head can be neglected because the seepage velocity is very small. So the total head at any point can be as follows. So you may refer to this equation. Total head is equal to U over unit weight water plus Z. Alright, this is the pressure, elevation, and total head for flow of water through soil. If you see here, this is the equation. Q is equal to V times A. V is velocity. So velocity is K times I. Alright, so how to determine Ki? So K is coefficient of permeability. I is hydraulic gradient. I is delta H here over L. Okay, delta H is HA minus HB. L is drainage path. As I mentioned before, the loss head between 2 points AB can be given by delta H is equal to HA minus HB. The head loss, delta H, can be expressed in non-dimensional form as I, which is hydraulic gradient, is equal to delta H over L. L, distance between point A and B, the length of flow over which the loss of head occurred. Pressure head and hydraulic gradient. In most soil, the flow of water through the void spaces can be considered as laminar. V proportionately to I. In fractured rock, stone, gravel, and very coarse sand, turbulent flow condition may exist. Alright guys, flow of water through soil may either be a laminar flow or turbulent flow. So what is the difference between laminar flow and turbulent flow? Each fluid particle travels along a definite path, which never crosses the path of any other particles. So we call it as laminar flow. Paths are irregular and twisting, crossing at random, so we call as turbulent flow. Usually this one is for rock and very coarse soil. Alright, this is the Darcy law. Darcy law states that the volume of flow of the pore fluid through the porous medium per unit time is proportional to the rate of change of excess fluid pressure with distance. So V, which is discharge velocity, is equal to Ki. K is coefficient of permeability, I is hydraulic gradient. Soil is a porous medium. Just now we're talking about the velocity. But this one, we're talking about the flow rate. Q is calculated as the product of flow velocity times total cross-sectional area. So Q is equal to V times A. Alright, so A is cross-sectional area. Assume a column of soil and water flowing through. Look at this. If the water flow from A to B, so you have to determine the discharge. Discharge is V times A. Alright, thus flow rate is equal to Q is equal to A times K times I, because V is equal to K times I. Look at this equation. V is equal to Q over A, or Q is equal to VA, right? Where V is also equal to KI. Right, so you may refer the equation here. Q is equal to V times A. V is equal to Ki. Okay, what is the permeability? Permeability is a measure of how easily a water can pass through a soil. Look at that. This is for loose soil and this one is for dense soil. For loose soil, the water is easy to flow. For the dense, it's difficult to flow. Loose soil, high permeability. Dense soil is low permeability, right? Therefore, different soil have different permeability. Gravel and sand are more permeable than silt and clay. So permeability through soil is important for the following engineering problem, because we want to determine the drainage characteristic, design a landfill site and investigation of contaminated land, calculate the seepage through the body of a dam. The stability of slope and retaining structure can be greatly affected by the permeability of the soil involved. Determination of rate of settlement of a saturated compressible layer. Filters made of soil are designed based upon their permeability. And the last one, calculation of uplift pressure under hydraulic structure. And their safety against piping. Piping is the erosion of the soil, known as soil piping, can lead to pressure of the structure and to sinkhole formation. Alright, coefficient of permeability K, we call as the hydraulic conductivity, is the capacity of the soil to allow water to pass through it. Hydraulic conductivity is generally expressed in centimeter per second or meter per second. Coefficient of permeability or hydraulic conductivity K varies widely for different soil. The hydraulic conductivity of unsaturated soil is lower and increases rapidly with the degree of saturation. You may see here, this one is the soil types and the coefficient of permeability. For example, here is the clean gravel. The K value is between 1 to 100 centimeter per second. And for the clay, the K value is about 1 times 10 power of negative 6 centimeter per second. So if you see here, when the soil size is smaller, the value of K is smaller. Alright, if the soil is coarse, the value of K is greater or larger. The value K is affected by several factors. Porosity of the soil. The porous the soil, the higher value of K. Particle size distribution. Okay, this one is referred to the size, whether that one is coarse or fine. For the coarse soil, the K value is higher compared to the fine soil. Shape and orientation of soil particle. If you see, if you compare the dense soil and the loose soil, you will see that for the loose soil, the K value is larger compared to the dense soil. Degree of saturation and presence of water, type of cation, and thickness of adsorbed layer associated with the clay minerals. So means that if the thickness of clay minerals is high, so means that the K value is lower. Alright, viscosity of the soil, which varies with the temperature. This one you may refer to the table because the different temperature will give you the different value of K. Now I want you to compare between gravel, sand, silt, and clay. For example, here, firstly you pour the water to the all of the sample. Okay, right. So after 2 minutes, the gravel, the soil will start pass through the water, pass through the soil, and then after 2 minutes, look at that. Just the water very go fast, right? And you see here after 2 minutes, all the water can go out from the soil. And here for sand, after 2 hours, and for silt after 200 days. For clay is for 200 years, for example. So means that the value of K for gravel is greater than sand, K sand is greater than silt, K silt is greater than clay. Effect of temperature. Okay, the value of coefficient of permeability K will be affected by changes in temperature. This is theoretically laminar flow condition for saturated soil mass. K proportionally to unit weight water over viscosity of water. The correction for the effect of the temperature may be obtained as follow. K correction or permeability correction is equal to K times KT. K corrected, K is the value of K corresponding to a temperature. KT is temperature correction coefficient. Okay, this one for KT you may refer to the table. Alright guys, this is the table values of temperature correction coefficient KT. So it's different temperature will give you the different value of KT. For 20 degrees Celsius, the KT is 1. When the soil the temperature is higher, for example 70, KT is become 0.410. So means that the value of K is smaller when the temperature increase, right? If the temperature is reduced, the K value is larger. Look at this for 0 degrees Celsius. Alright, now we go for the laboratory measurement. Coefficient of permeability K can be measured using field tests or tests conducted in the laboratory. So we have two tests, two laboratory tests. First is constant head test and second is falling head test. Okay, so the difference between constant head and falling head, for constant head, this one is for coarse soil. For falling head is for fine soil. Okay, in the laboratory, error may occur due to the presence of air bubbles in water, variation of sample density and porosity, and variation of temperature and viscosity of water. The accuracy of value of K determined in laboratory depend on several factors. First factor is temperature of the fluid, viscosity of the fluid, trapped air bubbles, presence in the soil specimen, degree of saturation of soil specimen, migration of fine during testing, and last one is duplication of field condition in the laboratory. Alright guys, this is the apparatus for constant head. The test is suitable for coarse-grained soil such as sand and gravel. Right? You may look at the YouTube link here. Okay, you may try look at how the test is being conducted. Alright, this is the test procedure for constant heat test. Okay, you may refer the procedure, and this is the equation. This is the equation that we are going to use to determine the coefficient of permeability for constant heat test. Q times L over A H T. Okay, so what is Q? What is L? What is A, H, and T? Right? So what is that? Alright, this is the schematic diagram of constant head apparatus. This is the equation. Coefficient of permeability K for constant head. K is equal to Q times L over AHT. So K is quantity of water collected in time. L is distance between manometer tapping point. So this is the manometer tapping point. For example, we have, this one is A, B, C. Okay, so the difference between manometer tapping point A and B, the different distance here. Alright, so B to C, so the difference between B and C tapping point. Alright, so T is time taken to collect Q. Alright, so look at here how to determine the H and L. Okay, for example, this is manometer A, B, and C. So H1 is A minus B. So L1 is, look at this, A minus B. So you will get L1. So H2 is B, the length minus C. So you will get a H2. Okay, the height B minus the height C. So you will get H2. The L is the distance between tapping point B and C. So you will get as L2. Alright, so the H is the height between B and C. You will get the H2. Alright, so this is how to determine the value of L and H. Alright, so how about A? A is cross-sectional area of sample. So for example, this one is cylinder. So pi d squared over 4. Okay, to determine the circular cross-sectional area. Alright, this is Darcy equation of flow. Q is equal to AV. Yes, you know that V is equal to KI. So from this equation, Q is equal to AKI. So you find the K is equal to Q divided by AI. Okay, so from this equation, K is equal to Q times AI. Alright, so as you know that the flow rate Q is equal to Q over T. Hydraulic gradient I is H over L. So if you see here, this one is Q. So you put the Q value over T here. I is H over L. So you will get this equation. So, and the final equation, K is equal to QL over AHT. So this is how we get the equation from the Darcy equation for constant head. Okay guys, refer to the exercise. The following data were recorded during the constant head permeability test. So when we're talking about the constant head permeability test, you have to use this equation. K is equal to Q times L over AHT. Alright, internal diameter is 75 mm. So from the diameter, you have to determine the value of cross-sectional area. Cross-sectional area is pi d squared over 4. Okay, head loss over a sample length of 180 mm. So sample length, so the L value is 180 mm. Head loss H is 247 mm. Quantity of water collected in 60 seconds is 6 to 6 ml. So calculate the coefficient of permeability for salt. So firstly, what you are going to do is you have to look at the unit SI. So for example here, this one is mm, so this one is ml. So what you are going to do is you have to convert the ml to mmq. Alright, so okay, calculate the coefficient permeability for soil. So the value of K, you may check 1.72 mm per second, or you also can use the meter per second. Alright guys, look at the second exercise. A per millimeter containing a soil sample with a diameter of 100. So diameter 100 mm and 200 mm length. So this one is diameter to determine the area, and this one is L. When the water flow through the soil sample, the water collected in 1.2 minutes. So this one is T is 159 ml. So this one is Q. The loss of head between manometer tapping point is 85 mm. Okay, determine the coefficient of permeability of soil in meter per second. So firstly, what you are going to do is you have to convert everything in meter, alright, and second. So this one is in minutes. So 1.2 minutes times 60 second. So you will get the seconds. So for this one is in meter. So 0.2, 0.1. So for area, pi d over 4 diameter. So 0.1 squared over 4. Alright, that one is for area. And you can look at this one is Q in ml. So you have to convert into meter cube. Okay, meter power of 3. So the answer K is equal to 6.62 times 10 power of negative 4 meter per second. So you may try now. Alright guys, this one is laboratory testing for falling head test. This is suitable for fine grained soil. You may follow the YouTube channel here. You click the link to look at the falling head test procedure. Alright, so look at this. This one for falling head test, you have to use a new equation. K is equal to AL over AT ln times H1 over H2. So H1 is the height, first height. Okay, height 1. Okay, before. This one before. H2 is height after. H1 over H2. Alright, look at that. L. L is the length of sample. The length of sample is L. T is time taken. Okay, look at this. You have a small a and a large A. Alright, so A small is the cross-sectional area for standpipe. Okay, A here, the big A, large A here is the cross-sectional area for soil sample. Alright. Okay guys, this one is the procedure for falling head test. Okay, usually the standpipe is refilled and the test is repeated for a couple of times. Okay, this is the permeability, coefficient of permeability of soil is determined by using the equation. Alright, this is the equation. K is equal to AL times ln H1 over H2 divided by A times T. Alright. Alright guys, this is the illustration for falling head test. Okay, we have 1, 2, 3. If you notice here, this one is standpipe of different diameters. So usually for the test, we will take more than one times test. So we take the sample. We take the sample from the different diameter. So maybe 1, 2, 3 times. Three samples. Okay, so I look at the value of A. Small a is cross-sectional area for standpipe. So we have 1, 2, 3. So every standpipe have a different value of A. Alright, so this the larger A is cross-sectional area for sample. Alright, so look at the value of H1 and H2. For example, you start test from H1. This is the initial height. And then after that, you open the valve and you let the water go down. And then you stop. You close the valve and then you will get the new H2. So you will get H1 and H2. And then you will know how much time taken from water flow from H1 to H2. Alright, so the length here is, look at that, the length of sample, yeah. And then from all the information here, you will insert to the equation here. Alright, so you may use this equation or this equation. Alright guys, this is the derivation of formula from the Darcy equation. Q is equal to AB equal to AKI because V is KI. So for this one, you have to do something here. This is how to derive the formula. Then lastly, you will get this formula or this formula. So you may use either one. Alright, so guys, this is example for falling head test. During a test using falling head thermometer, the following data were recorded. Determine the average value of K. So first is diameter of sample is 100 mm and length of sample is 150 mm. So this one is L, this one is the large A. Alright, so this one is a standpipe diameter. So we have the small a1, small a2, small a3. So you have the initial H1 and final H2. So you H1 and you have H2. The time interval is T is here. So from this data, you may use the equation for falling head test. Alright guys, so for the solution, you look at the equation here. AL times ln H1 over H2. So you look at here, the level of standpipe. So you have the H1 and also H2. So H1 is 1200 over 800. So H1 1200 over 800. Oh, H1 over H2. Ln L is 150 mm. A is the cross-sectional area for standpipe. So pi d squared over 4. First pi times d, which is 5 squared over 4. So you will get the small a, and then the big A or large A. So you have to determine by using the cross-sectional area for sample. L is 150 just now. So 150. So pi times 0.15 or 150 mm. It depends for you if you want to use the mm or meter. For this one we use mm. So pi times 150 squared over 4. So you will get the value of A. T is time interval. For example, here is 82. Alright, so to determine the value, here is ln H1 over H2 is log 10. Okay, you calculate for log 10. Okay, so you get the value of K is equal to 1.854. So times of 10 power of minus 3. So and then you will determine the value of K for each different standpipe and different H. Okay, and then you will have to determine the average value of K. For example, here the average value of K is 1.85 times 10 power of negative 3 mm per second, or 1.85 times 10 power of minus 6 meter per second. Alright guys, now we finish our week 5, so I will give you the tutorial after this. Remember guys, you can do anything you set your mind to by Ben Franklin. Thank you guys, good luck.